No. Okay. So we're gonna move on, and one other slight variant we're gonna look at is what's called persistent carrier sensing. Is this right? Yeah. Okay. Okay. Right. P-persistent carrier sensing. And we're going to make one slight modification. When we talked about aloha, we always did exponential backoff. For transmission, right? And now with P-persistent, do exponential backoff with probability P. Or is it not do the exponential? I just want to stay consistent with my notes. Yeah, sorry. It's going to just to be consistent with the notes. Do an immediate transmission. Back off exponentially with probability 1 minus B. Okay, and we're assuming the line is being sensed. Okay? Everybody gets the idea? I think if there's any analysis worth doing on this in class. Let's see. Okay. Let me just make some comments about it. If P equals 0, okay, so you back off exponentially with probability 1 minus P, it's equivalent to aloha. Right, for aloha, you sense the line If it's busy, you back off exponentially. Right. Okay, so one difference between aloha is when we talked about aloha, you sort of imagined you were backing off exponentially, and then you would check the line, and if it was busy, you'd back off exponentially again, right? And if it wasn't busy, you would transmit. Okay? And there was no notion of continually checking the line when we were using aloha, right? You sort of imagine you check the line, and then you'd stop and just sort of ignore it, right? When we're talking about P persistent, we're talking about a carrier sensing environment where devices can continually sense. Okay, so now the point is I'm looking at the line, I'm watching it, and I see somebody else transmitting, and as soon as they're done, the line's free. I could start transmitting, right? So actually, let's talk about that case first. So P equals 1, as soon as the line becomes free, all waiting devices transmit. So if you have a lot of devices, or even two devices waiting to transmit, their transmissions are going to collide, right? At the same time, they're going to see the line go free, and they're both going to start to transmit, and you know, their transmissions are just going to collide. Hence the need for this random backoff. Okay, so with aloha, you do the backoff all the time. So this case is easy to see, but if you have lots of devices, if more than one device to transmit, okay, guaranteed collision. Right, and the idea is if you pick the right P, make P small enough, there's a chance that one device will go right away, while all the other devices do the exponential backoff. So there's a chance that you're making very efficient use of the line. Whereas if you always just do the exponential backoff, then you're almost guaranteed to be a gap in time when the line's not used. Okay, so it was a small attempt to do a little additional optimization. Okay, and the only other comment I wanted to make is when P is 0. Why is this just like aloha? I mean, it's a slightly different scenario, but why does it not matter? So here's the line being used, okay, and then the line goes quiet, right? And let's say I got a device running the aloha protocol, and a device running 0 persistent, right? So this device can sense the line the entire time, right? And this device doesn't. It doesn't look, okay? Until its timer expires. So what does this situation remind you of? One device is looking, one device can't look, can't see. Huh? The twins, right? It's the exact same scenario, right? You've got the aloha device. You know, it can check the line at an arbitrary time whenever its timer expires, and if there's a transmission going on, it says, okay, I'm gonna reset my random timer, and I won't look again until the timer expires. Whereas this device is watching, and as soon as the point in time comes when the transmission ends, it says, okay, now I'm going to set my timer. Okay, so this device's timer is guaranteed to start here, whereas aloha, when you sort of cross this point, its timer's been running for a certain amount of time. But because the timers are exponentially distributed, neither version has an advantage over the other. Right? It's the exponential timer is memoryless. Both timers are running at this point in time, so they're both equally likely to expire later on. So it's just like the scenario with the blind twin and the seeing twin. That's, you know, so maybe you understand it better in this context, and now you can see why the blind twin can jump as far as his brother. Okay? Any questions on that? Right, so if you set p to some other value besides 0 or 1, like I said, you'll reach this point in time, and with a certain probability, some of the devices will start transmitting right away. If more than one does, you get collisions. And otherwise, if none of them do, they back off, and it's just like regular aloha. Or if only one transmits, it gives you a slight advantage over just using aloha. When p does not equal 0, it gives you a slight advantage over aloha, right? Because one device might start transmitting as soon as the line becomes free. Or if you set p incorrectly, if you make p too large, and there's a very large probability that a bunch of devices are going to transmit right away, and they're all just going to collide, right? And that's not good. I mean, you're not making use of the line in that case. Okay? Any questions or any confusion on this? Okay, we're gonna move away from a continuous probability perspective of this and move to a discrete probability perspective. So, if you think about when you use a slotted protocol, okay, we were talking about the way it's implemented in practice is you have this slot, and if your timer goes off in this period of time, right, then you're going to transmit in the next slot, right? And if the slot length is t, and the exponential timer is lambda, okay, then the probability of transmitting in the next slot is 1 minus e to the minus lambda t, right? That's the probability that your exponential timer goes off in that interval. You can just call that p. Okay? You can just because the timers, whether or not you transmit in this slot, because of the memoryless property, it's independent of whether or not you transmit in this slot, is independent of whether or not you transmit in this slot. This timing process is an ID process, so this P is just a Bernoulli process. Okay, in other words, I make the same decisions if I say, I'll flip a coin, and with probability P equal to this 1 minus e to the minus lambda t, I'll transmit in the next slot. Okay, it's the exact same process. Okay, the only reason I taught it before with the exponentially distributed random variable is because it matched up with aloha and with aloha with carrier sensing. Okay, but the slotted aloha protocol, really all that matters is you flip a coin. If that coin is heads, transmit in the next slot. Okay. Who gets what I'm talking about? Who doesn't get what I'm talking about? Who's not paying any attention? Jeez, a single hand. Who gets what I'm talking about? It's like, kind of. Not really. Okay, you understand that the probability that the timer goes off this slot is this 1 minus e to the minus lambda t. Right? That's the probability that the timer goes off in this slot. That's the probability that I transmit in the next slot. Now, whether I choose to transmit in this slot and choose to transmit in this slot, that depends on whether or not my timers go off in these slots and these slots. Right? If you look at what the probability that the timer goes off in this slot, conditioned on the probability that the timer goes off in this slot, why don't I write this down? Let x sub I be a random variable. It's 1 if timer goes off in slot I and 0 otherwise. Okay, and all I'm saying is the probability that xi equals 1 is 1 minus e to the minus lambda t. Okay? So I'm calling this value P. Probability that xi equals 1 given xi minus 1 equals 1. What's the probability that my timer goes off in the ith slot given that it went off in the I minus first slot? Okay, and I'm claiming you can intuitively see that it's just going to be the probability that the xi equals 1. It doesn't matter if it goes off in the I minus first slot. It's a memoryless process. So what happened in the past, right, when I get to this point in time and I ask what's the probability that the timer goes off in this slot, doesn't matter when the last time was that the timer expired, because it's an exponentially distributed random variable that's determining the amount of time. Okay? And this is effectively saying these two things are independent, right? If I multiply both sides by probably the xi minus x sub I minus 1 equals 1, I get, so multiply both sides by probability xi minus 1 equals 1, you get probability that xi equals 1 and xi minus 1 equals 1 equals probability xi equals 1 times the probability xi minus 1 equals 1. Right? They're independent. Now just take this identity, rewrite it as, the and divided by probability xi minus 1 equals 1, you get that. And intuitively that makes sense. That this is saying they're independent. The probability that xi equals 1, given that xi minus 1 equals 1, is just the probability xi equals 1. It doesn't matter what the value of xi minus 1 was. Okay? So we have a process where the probability you're transmitting in a given slot is P, and it's independent of the previous one. That's just the Bernoulli process. It's like flipping a coin and it comes up P. That's all I'm trying to say. Okay, so we're gonna go to this discrete case because it's much easier to analyze, and we're gonna complicate the topology. So before we had all devices equidistant, if two devices transmitted, you'd always get a collision. Okay, we're gonna have we're gonna go to a wire network scenario. With what are called hubs and switches. Okay, what we're talking about now is a little bit dated because hardly anyone uses hubs anymore. Switches is the big thing. They're so cheap now that you never need to use a hub. But what is a hub and what is a switch? So hubs and switches connect multiple devices together. So for instance, here, let me draw devices as a square. So these are devices that transmit. Okay, so this thing here is a hub or a switch. And the Ds are your transmitting devices. Your computer. Okay, so you maybe have heard of switched Ethernet, or these computers are switched, that sort of thing. Anyways, right when you get these computers, you plug the Ethernet jack in somewhere and you plug it in somewhere else, and that thing you're plugging it into somewhere else is connecting your computer to the rest of the world. It's connected, we'll say for now, by a hub or a switch. Okay, and the difference is hubs have no intelligence. And repeat the packet. Repeat the transmission packet. I'm going to wind up saying packets a lot. So transmission / frame / packet. Really all the same thing. Okay? They're going to repeat transmission / frame / packet on every wire connected to it. except the wire the transmission came in on. Okay. Switches know the destination and forward only on that wire. On the wire that reaches the desired destination. Okay? So, suppose I have a device D1. Okay, so I've got a bunch of devices. Okay? And suppose device 1, let's see. Let's do D1, which is to communicate with D2. And D4 wishes to communicate with D5. Okay? And suppose let's assume the slotted transmitting environment. And D1, D4 and make the transmissions during same time block. Okay? So, if X1 and X2 okay, so we're going to vary the form of X1 and X2, whether they're a hub or a switch, and we're going to ask, do these transmissions collide? Okay, so if X1 and X2 are both hubs, where hubs broadcast everything, right, then D1, if X1's a hub, D1's transmission is going to go to the hub, and the hub is stupid, right, has no intelligence, it's just going to forward the transmission everywhere. So it forwards it to D3, it forwards it to D2, forwards it to X2, and X2 is also a hub. So it's going to forward the transmission on all the wires. Okay? And D4 also transmission to D5, and it forwards it on this wire, and hence there's a collision. D4's packet doesn't get through. Okay? And also it traverses this wire because this is a hub, so it goes all the way. And this is a hub. So again, D1 wants to transmit to D2, so it'll also be forwarded on this wire and on this wire, and so you'll again have collisions, right? So the packets collide, right? What if X1 is a hub and X2 is a switch? Okay. Now D4 wants to communicate with D5, so its transmission will traverse just these two wires because X2 is a switch. Right? It's smart enough to know that there's no reason to transmit the communication between D4 and D5 on this wire over here. Right? And D1 is going to want to communicate with D2, and X1 is still a hub. So that transmission is going to, again, go across these wires. Okay? But when it gets to X2, X2 knows that D2 does not lie in this direction, so it's going to suppress that transmission any further. Okay? So there's no interference for the D4 to D5 transmission, and the D4 to D5 transmission doesn't go past that point either. So there's no collision. Okay? If both are switches, also you're going to have no collision. I mean, X1 is just simply not going to forward that transmission to the switch. Okay? So I should have said one other thing. Collision happen in wires. Happen on the wires. Okay, so not in the switch or hub. So a switch can actually handle, if it has two transmissions coming in simultaneously off two different wires, it can distinguish the two. So for instance, in a switch, if you've got one transmission that you want to go that way and another one that you want to go this way, there won't be any collision. Okay, if one transmission is going across the switch this way and one transmission is going across that way, no collision. The switch can handle them both at the same time. But if you have two transmissions, okay, one's going this way and the other one is supposed to go that way, that will be a collision, not because of a problem in the switch, but because of a problem on this wire. Okay, this wire has to carry two packets at the same time, and so there'll be interference. Okay? Okay, if you have switch hub, then what happens? So this is a switch. So we're doing D1 to D2. So D1 will be sent only to D2, and D1's transmission won't be carried on this wire. And D4 to D5 will be carried on, will be broadcast because X2 is now a hub, and it goes to this X1, which knows to suppress it. So it's still not a problem. So there still won't be any collisions. And no collisions if both are switches as well. Okay? Okay. So now you can start asking these kinds of questions. Suppose I have this topology. Okay, where this is okay, I didn't do it very successfully, but I wanted to draw. Let me start again. Sorry. Okay, so I'm building up a network that's connected up in a tree-like structure. Okay, so these are the devices. and they're connected to hubs or switches, which are connected to hubs or switches, which are connected to some root hub or switch. Okay, so there's a path between any pair of devices. Okay, so here I've drawn a tree of depth 3, and with each hub having a downward degree. Of 3. Okay, but I can generalize it to K. Okay? You know what, let's just consider a tree of depth 2. So let's do this. Here you have a root hub, okay? You have K outgoing edges here, okay? Each of these edges is connected to a hub. Okay, again, each of these hubs has K outgoing edges. Okay, and then let's just put devices here. So it's a depth 2 network. Okay, we'll have K devices on each of these. Okay, and let's let the probability that a device transmits in a given slot be P. Okay, and let's consider a specific round, or a specific slot. Okay, and let S sub I, let's make it T sub I. T sub I be an indicator random variable which equals 1 or 0. It equals 1 if device I attempts a transmission during our selected slot, 0 otherwise. And let's define S sub I to be 1 or 0 if 1 if device has successful transmission. Successful transmission. 0 otherwise. Okay? So he follows me. And one other thing I just said is we're numbering these devices. Let's go. Let's number them 1 through K. 1, 2, dot K, and then the next batch would be K plus 1. You know, under the next hub, up to 2K, etc. And then finally, since we have 2 levels of this thing, the last device would be number. Okay? People following? Every device is assigned some number. So we go from, if we have K squared devices, we'll go from 1 to K squared. Okay. Where devices 1 through K are under this same switcher hub, devices K plus 1 through K are under the same switcher hub, etc. Okay? And what I've said over here is that the probability that T sub I equals 1, the probability that the device transmits in a given slot is going to be P. Right? Okay? And what we want to know is what's the probability that a device is successful in its transition? Okay? And that'll depend on whether or not these forwarding elements are switches or hubs. Okay? Okay? So let's focus on device 1. Okay? So suppose device 1 wants to transmit to device I, where, well, it's not going to transmit to itself. Where 2 is less than or equal to, well, yeah, before I say this. Let's also say, suppose the destination is chosen uniformly from a set of other devices. Okay. So what I mean is the destination of device 1's transmission, I should say. Right, so device 1 is going to make a transmission, maybe, with probability P. And when it does so, it's going to choose its destination uniformly at random. Uniformly at random. Okay, so we'll also define let D be the destination device of device 1's transmission. Okay, and all I'm saying is that the probability that D equals some I, the probability the destination device I is going to be what? If the destinations are chosen uniformly at random. So I heard some things that sounded right. 1 over. Yeah. For I greater than 1. Right. Probability that D equals 1 is 0 because it's not going to transmit to itself. And there are k squared minus 1 other devices. You're equally likely to transmit to all those. So it's 1 over k squared minus 1. Right. Okay, so before we actually start computing these probabilities, let's first think about the scenario. So suppose, let's say E equals 2. Okay, and all forwarding elements are hubs. What has to be true about other devices what has to be true about the transmissions of other devices in order for device 1's transmission to be successful during this slot? Yeah, no other devices can transmit. If any other device transmits, that transmission will collide with device 1's transmission. right? So what's the probability that device 1 has a successful transmission? To device 2. So I want to know what's the probability that, let's see, the device 1 transmits, it's transmitting to device 2, and its transmission was successful. What's that probability? Just let me, don't think about the math for a second. Just think about what the scenario going on is here that we're talking about. What has to happen? Think about it from the perspective of the protocol. During that slot, what are all the things that have to happen to make those random variables all true? What does device 1 do? It has to transmit, and what else? It has to choose device 2. Right, so device 1 has to transmit. Must transmit to device 2. And what else? In order for the transmission to be successful. I mean, we said it. No other device can transmit, right? Okay, so now, what is that probability? What's the probability that device 1 transmits? P. What's the probability that it transmits to device 2? 1 over k squared minus 1. We can think of those as being dependent, because you can imagine device 1 can choose whether or not it's going to transmit and independently choose the destination where it's going to transmit to. So it makes those two choices independently. If it doesn't transmit, where the destination is doesn't matter. Okay? And also independently, the other devices act independently. So what's the probability that no other device transmits? Yeah. Right? No other device transmitted. Okay? And I would claim that P of T1 equals 1, D equals J, S1 equals 1, equals this value also. For any J greater than 1, right? The destination really didn't matter in this case. Wherever it chose to transmit to, there's the same probability. No other device can transmit. Okay? So, in this case, where forwarding devices are all okay, we want to compute the probability that SI equals 1. Okay. First thing I would claim is that this equals probably that SI equals 1 and TI equals 1. Right? People see that? I mean, you can't have a successful transmission without a transmission. Right? I mean, really what you'd write is and this is 0, right? The probability that you have a successful transmission and you don't have a transmission is 0. So the probability that SI equals 1 equals the probability that SI equals 1 and TI equals 1. Okay? And this is just the sum from J equals 2 to K squared of probability SI equals 1, TI equals 1, D equals J, right? Summing over all possible destinations. Okay, so you're just going to get, it's going to be P times 1 over, times 1 minus P to the K squared minus 1. Which also makes intuitive sense. In this case, it didn't matter what the destination was. If device 1 transmitted and any other device transmitted, you were going to get a collision, right? So you could have sort of jumped ahead and just seen this. But when we start considering switches instead of hubs, it's not going to be that simple. So now let's look at the case where the forwarding elements are switches. Okay, and suppose device 1 is going to transmit to device 2. Okay, now we're talking about switches. So what can we say about the other device's transmissions in order for this device's transmission, in order for device 1's transmission to be successful? What can we say about the other device's transmissions?
No one else can be transmitting more.
Yeah. Okay, so nobody else can transmit to device 1 or device 2. That's clear. No other device. Can transmit device 1 or 2. Any other restrictions? No, that turns out to be sufficient, right? All we care about is making device 1's transmission successful. And we said everything is a switch. Switch, 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 switch. Right? So device 1 is going to transmit to device 2. Those transmissions are only going to go on those 2 wires. And as long as anybody else doesn't transmit to device 1 or device 2, there won't be a collision. Right? You know, if device 3 transmits to device 4, that's okay. Again, the switch can handle multiple transmissions at the same time. It's just the wires that we have to worry about. And any other device transmitting anywhere, even if there are other transmissions collide, as long as it doesn't collide with device 1's transmission, device 1's transmission will be successful. Okay? So what is the probability that device 1 transmits? It's transmitting to device 2, and the transmission is successful. So what's that? Yeah, Ari?
What if device 2 tries to stay?
Yeah, right. No other device can transmit to device 1 or 2. That's right. And device 2 cannot transmit. Thank you. Okay. So for this scenario, what's the probability? Device 1 is going to transmit with probability P, right? Just like before. It's going to transmit to device 2. That's going to happen with probability 1 over K squared minus 1. Right? But now we have to do everything else we said. No other device can transmit to device 1 or 2, and device 2 cannot transmit. Right? Okay, so device 2 cannot transmit. That's 1 minus P. Right? And for every other device, it cannot transmit to device 1 or 2. So how do we say that? Let me write it here, and then I'll show you what I'm talking about. Okay, I claim that's the last term. Sorry. To the k squared minus second power. Okay? So what is this saying? K squared minus 2 raised to the k squared minus 2 power, because I have k squared minus 2 devices being considered. Right? Device 3, device 4, device 5, all the way up to device k squared. What I'm going to say inside here has to be true for all of them. And what I'm claiming is that each of those devices either does not transmit, okay, it does not transmit with probability 1 minus p, or it transmits, and as its destination, it chooses any of the k squared minus 3 possible destinations other than self, device 1, or device 2. Right? So out of the k squared minus 1 possible choices of where it can send to, k squared minus 3 of them are okay. Yeah.
Can it transmit to itself?
No. We're assuming in the model we said that every device, this is true for every device, it's never going to transmit to itself. I mean, that's silly, right? When you decide to transmit, it's going to be to some other device. Okay? So do people understand the logic? This device has two choices. Transmit, don't transmit, or do transmit and limit the range of devices to which you're going to transmit. Okay? Everybody follow that? Okay. What about the probability that T1 equals 1, D equals K plus 1, or let's do K squared. K squared, S1 equals 1. Hang on. Before we write that out. Let's just say, suppose D equals K squared. We're using switches. How about now? Which other devices can transmit? Okay, so if we're sending to K squared, device 1's transmission has to go like this. Right, so who else cannot transmit? Yeah, anyone connected to this, well, switch. Right, anyone connected here, well, depends on their destination. If anyone in this switched environment wants to send to any of these other switches, it's going to have to traverse this wire, and that wire is needed by this transmission. So anybody in this grouping, if they want to transmit, they have to transmit inside this interval, but not to K squared. Right, to anything other than K squared inside here is okay. This one, same. These devices, same thing. They can transmit to any other device inside this region, except for device 1. And for the ones in these other regions, they can transmit anywhere except to any devices in this region or any devices in that region. Okay? So, if D equals K squared, the expression is a bit more complicated. So all right. Well, let's write that down. Okay. let's see. Device k squared cannot transmit. Right? Devices k squared minus k plus 1, just k squared minus 1, can only transmit amongst themselves. Okay? Devices 2 through k, 2 to k, can only transmit amongst themselves. And devices k plus 1 through k squared minus k can also only transmit amongst themselves. Right? So if this one transmits amongst itself, there are k minus 1 allowable destinations for both of those cases. Right? Their k minus 1 destinations are allowed to transmit. And these guys can only transmit amongst themselves. There are k squared minus 2k minus 1 allowable destinations. Right? There's k squared destinations in total. You can't transmit to the first k. You can't transmit to the last k. And you also can't transmit to yourself. Okay? Everybody follow? Okay, so now we're ready to compute the probability that P1 equals 1, P equals k squared, S1 equals 1. That's just going to be P for device 1 transmitting, right? 1 over k squared minus 1 for the destination being device k squared. Okay? And now there are k squared cannot transmit. Okay, so maybe I can even describe what each of these are. Device 1 transmits, okay, to k squared. K squared does not transmit. Okay, now I've got 2k minus 2 devices that are only allowed to transmit to k minus 1 destinations. Okay, so each of those devices can either choose not to transmit or it transmits, and there are k minus 1 allowable destinations. Right? And I said there are 2k minus 2 such devices. So each one has that option independently. And then finally, the remaining k squared minus 2k minus 1 allowable devices can only transmit amongst themselves. And there are, sorry, the remaining k squared minus 2k devices are allowed to transmit to k squared minus 2k minus 1 possible destinations. So each of those devices, either they don't transmit or they do transmit, and one more time, k squared minus 2k minus 1 over k squared minus 1 to the k squared minus 2k. Okay, so What I'm saying is there are 2k minus 2 different devices, okay, that are independently going to have this choice. They can either choose not to transmit or to transmit to some restricted set of destination. Yeah?
And the third term, isn't it p to k minus 2 with this?
Sorry, P
The third term, 1 minus p.
plus P,
K minus
2k minus 2.
2. K minus 2.
K minus 2. Why? Oh, because,
When if you take devices 2 to k, device 2 can only transmit to devices 3 to k.
yes, that's right. And device, yes, that's true. So yeah, sorry, so there's k minus 2 allowable destinations. Yeah, yeah. You're not allowed to transmit yourself, right? Thank you. Okay, so I want to point out something important that sometimes. Well, let me finish explaining what all these are. So this is a device does not transmit. Or, and this is saying transmits and destination is one of k minus 2 allowed. And this is because there are 2 k minus 2 such devices. Okay? So just a quick question. Why is it 1 minus p plus p times whatever this thing is to the L instead of 1 minus p to the L plus p times wherever this stuff is to the L? Why did I put this whole term raised to this 2k minus 2 instead of this raised to the 2k minus 2 plus the other term raised to 2k minus 2? I mean, they're both saying do this or that. What's the difference? Why is this one correct in this instance and not this one? What are they saying?
In the second case, all the devices are either transmitting or not.
Right. Right. The first case says every device gets to make its decision. Every device can choose to transmit. Can choose not to transmit or to transmit, and every device can make that decision independently. Right. So you can have some devices that choose to transmit and some that aren't. Okay. This case is saying either they all don't transmit or they all do transmit. Okay. This says all devices either don't transmit or all devices do transmit. Who gets the difference? You put up their hands. All right, that's about half of you. So the other half needs to think about it some more. And if you're still confused, come to office hours. But it's equivalent to. Let me not. At the risk of confusing you more, let me just stop with that. Okay. And okay, and I would claim the following: if D equals 2 ... k, it's the same as the case as where d equals 2. Right, when d equals 2 or 3 or 4 or 5, 6, 7, 8, 9, up to k, okay, it's the same scenario that we had when d equaled 2, right? You're transmitting to something within the same local region. Okay, and if d equals k plus 1, k plus all the way up to k squared, it's the same case as d equals k squared. Okay, transmitting into a different region. You're crossing that root hub or root switch. People see what I'm talking about? And we looked at the case when d equaled 2 and when d equaled k squared. There was also the case when d equals 3 and 4 and 5 and 6. And all those other cases, from d equals 2 to k, it's the same as the case where d equals 2. All the cases for k plus 1 to k squared, it's the same as the case when d equals k squared. Okay? So the probability that S equals 1, again, the sum of the probabilities that the probability that S1 equals 1, D equals J, D1 equals 1. Okay, of course, we can always ignore this T1 because if S1 is 1, then it has to be the case that T1 is 1. Okay, so this works out to be that huge mess. Well, it's going to be, from my claim above here, it's going to be k minus 1 times the probability that S1 equals 1 and D equals 2, okay, plus k squared minus k times the probability that S1 equals 1 equals k squared. Okay, so if you want to put it all together, it's going to be p times 1 minus p times 1 over k squared minus 1. Okay, both cases have those terms in common, and then things start to differ, right? Yeah. So then there are k minus 1 cases where we have this this term on the bottom here. Where'd it go? There. 1 minus p plus p times k squared minus 3 over k squared minus 1. To the 2k minus 2 plus k squared minus k terms times 1 minus p plus p times k minus 2 over k squared minus 1 to the 2k minus 2 sorry, that's times 1 minus p plus p. Let me just do dot, dot, dot. Now to finish it off, I'm just copying this stuff up here. Okay? So it starts to get messy. Yeah, Ron.
The answer to why those three lines right there where you say, well, device K squared cannot transmit. Those are three lines below that.
Uh-huh.
Can you just explain those?
Yeah. Device K squared cannot transmit, right, because there'll be a collision. Devices K squared minus K plus 1 to K squared minus 1. So if I redraw the picture. Right. What I'm saying is the other devices under this switch here, right, they cannot transmit to any of these devices over here because then they will cross this wire. And that will interfere with device 1's transmission to device K squared. Right? So they can only transmit to K minus 1, K minus 2 other devices, which is not, they cannot transmit to K squared because that would interfere on this wire, but they can transmit locally. It won't interfere with any of the wires that the 1 to K squared transmission is using.
Each other K wires.
Switch. Yeah, in this case switch.
K wires.
Each switch has K wires going down and one going up to the root switch. Yeah, there are K devices under each switch.
So minus 2 because one itself, the other the device that's getting to device 1.
Yeah, the device, we're looking at the case where we're transmitting to K squared.
Right.
Device 1's transmitting to K squared. So yeah, these other devices they never transmit to themselves. But they also cannot transmit to device K squared, and they cannot transmit to any other device not supported by the local switch. Right? So that's those devices. Same thing over here. It's a symmetric situation for the other devices next to device 1. And for these devices here, they cannot transmit to device 1 or device K because it'll use those wires. But they can transmit amongst themselves.
They can go up to the switch, the root.
They can go to the root. Yeah. As long as you're not sharing wires, you're okay.
So you just, to get that K squared minus 2K minus 1, you subtract it. K squared minus K minus K.
K squared minus 2K minus 1?
Yeah.
Yeah, each device, there are K squared devices in total. Can't transmit to any of these K, and can't transmit to itself.
I thought that you had done K squared minus K minus 1 to indicate like the bounds of the device that you can't transmit to. That's what I was confused. You said K plus 1 through K squared minus K.
K plus 1, yeah.
So I thought that in order to get the allowable destination, to the difference of those two terms.
No. Okay. We're not really going to have time to go through the go through the last case I wanted to go through, which is what if you have a local switch, but the root is a hub. Okay, so we're not going to have time to work out all the probabilities, but at least we could set things up. So if D is 2, what then?
So you keep all processing on the local, so everything can go through that switch. It's just that, so everything's just based on that one left.
Yeah. Right. All other devices let's say no device can transmit to device 1 or 2. Right? But everything else would be okay. What if D is k squared? Yep.
That would leave their local switch.
Yeah, right. All devices have to transmit locally. And devices 1 through k, well, I could say and not to device 1 or 2, right? Because even the guys in the same regions k squared and 1. Sorry, devices 1 or k squared. Even devices those regions, even if they transmit locally, they still can't transmit to device 1 or 2. And just real quick, local hubs, root switch. Syn type. For D equals 2. Yeah, nobody can transmit to one through k, and 1 through k cannot transmit. Sorry, 2 through k. 3 through. Nobody else can transmit to 2 through k, and 2 through k cannot transmit. Right? Otherwise, 2 through k transmit, it gets broadcast locally. It'll kill one's transmission. If anybody else transmits to 2 through k, it'll get broadcast in 2 or k's local hub, killing in 2's local hub. 1's local hub, k's local hub. Okay. And if E equals k squared, the last case, no other device can transmit. Right? Any other device transmits, its local hub is going to broadcast that transmission. And, oh, wait. I might be wrong. We have a switch up at the top, right? That's not right.
At least those two local hubs, no one else can.
Nobody else can transmit, right?
Two local hubs.
And nobody else can transmit to those local hubs. And is there anything else? Yeah. Right? No other device can transmit to any of these. This 1 through k. 1 to k. Yeah.
Why are D equals 2 through k? Why isn't it 1 through k?
It is 1 to k. Thanks. Okay, and so again, you can work out all the probabilities. To ensure these facts. So no class next week, right? I'll be back in town Thursday, Friday. So if people really want to meet for office hours, maybe it's better to set up a time now.